Hi students, you see the induction mission is one of the important mission in electrical engineering, you know that. So here you see that in the induction mission is nothing but a simple circuit, electrical circuit. You see that the per phase equivalent circuit of induction motor. The per phase equivalent circuit of induction motor is this. Here you see the figure. This is a per phase equivalent circuit of 3-phase induction motor, right? So basically here from this per phase equivalent circuit, then the induction motor can be analyzed, right? What is meant by analyzation of the 3-phase induction motor? You see that? What is the analyzation of 3-phase induction motor? In what way you are analyzing the 3-phase induction motor? Yes, from the analysis we have to determine what is the torque, what is the power, what is the speed, right? These are the three important terminology in 3-phase induction motor. That is, the torque equation, power equation and speed equation. These three are related, very well, for any machine, electrical rotating machine. Now these three are related. What are the three? Power, torque and speed. That is angular speed, very well, right? Good. Right. In this equivalent circuit of 3-phase induction motor, of course, you can check this. Particularly, this particular circuit is a core-related circuit. In induction motor, stator and rotor, right? So this is a stator core-related circuit. Stator core-related circuit. And this particular thing is a stator winding related circuit. Stator winding related circuit. And this particular thing, rotor winding related circuit, right? So this is a core related circuit and this is a stator winding related circuit and this particular thing is a rotor winding related circuit. Then question is, what is this? This is very important. Understand? In equivalent circuit, the last one RL dash, what you here mentioned, the RL dash, what is that? That is very important. Of course, that is called, load equivalent resistance. What is that? Load equivalent resistance. What is the load equivalent resistance, sir? Yes, you know that here, the stator input is given here. Then the power is distributed like this. In R0 some power is lost. We are not utilizing that power. Whatever may be the stator input given, that input power is distributed at each and every resistor. Then what is the power loss at R0? That is nothing but stator core losses. The power loss at R0 is nothing but stator core losses. And what is the power loss at R1? R1 is a stator resistance, What is the power loss at R1? This is nothing but stator winding, stator copper losses. And the power loss at R2 dash, that R2 dash is nothing but, that's a rotor resistance equivalent. Of course, the power loss in R2 dash represent rotor copper losses. And this R0, R1, R2 dash, that's over. And the remaining power, whatever may be the stator input power, is distributed across R0, R1, R2 dash. These powers are considered as a losses. Those powers are not utilized, right? Then the power loss in RL dash, the power loss in this resistance is utilized. How this is utilized? In mechanical way, right? Now this total electrical energy is converted here as mechanically power. The mechanically power developed. Understand? So the power loss in RL dash, considered as a, what is that? Mechanically power developed. So here you can mention this, the power loss here, I can mention this. Come on, tell me. The power loss at R naught represent stator core losses. So here I mentioned stator core losses. Right? And representing here R1 is there. R1. The power loss in R1, of course the R1 related for stator winding. So the power loss in R1 is considered as a stator copper losses. And you come across this R2 dash, these are rotor equivalent resistance. Right? So in this case, the power loss in R2 dash represent rotor copper losses. Understand? So the stator input, of course, that is considered as a P1 stator input. The stator input is distributed as, you see, stator core losses, stator copper losses, rotor copper losses, and the remaining power is converted to mechanically power. The remaining power is in RL dash, of course that is called as a mechanically power developed. Yes, that power is utilized now. So in this case, the electrical energy is converted into mechanical energy. This particular RL dash is called as a load equivalent resistance. Of course, the load is connected to this induction motor. Of course, that load is equivalent to electrical resistance. That mechanical load is equivalent to electrical resistance. Of course, that is nothing but, yes, this is R2 dash into 1 by S minus 1. Already you know that R2 dash is nothing but rotor resistance. And S is nothing but, this is already known, that is slip of three-phase induction motor. Because you know that the three-phase induction motor is nothing but asynchronous motor. This motor does not, never runs with the synchronous speed. Always this motor is slipping from the synchronous speed. Some slip speed is there. Due to that slip speed, there is a slip, already know that. Understand? Yes, where S is a slip and R2 dash is a rotor equivalent resistance. Of course, RL dash is a load equivalent resistance. That's very important here. The power in RL dash is considered as a mechanically power developed. That is actually utilized power, of course. Yes, you can observe, the students, basically you can observe, where is the mechanical loss? Of course, in rotating machine, there is a mechanical losses, you know very well. How we can represent the mechanical losses in equivalent circuit? Yes, from electrical equivalent circuit, the mechanical losses are not mentioned because mechanical losses depends on mechanical resistance, not electrical resistance. So here, basically, from this equivalent circuit, we should not consider this particular mechanical losses, because in electrical circuit there is electrical resistance, where the mechanical losses depends on mechanical resistance. Mechanical losses means there is a friction losses, there is windage losses, like that. So that is a separate. After this mechanically power developed, then there is a mechanical losses. After subtraction of the mechanical losses, finally the output of the motor is coming. That is the power on nameplate. If suppose the motor is a 3 HP motor, the motor is a 5 HP motor, now that is a nameplate power. That is a final output. Understand? So whenever the stator input is given, the stator input power is distributed in this way. Number one, you see that the power loss at R0 is nothing but stator core losses. The power loss in R1 is nothing but stator copper losses. The power loss in R2 dash is nothing but rotor copper losses. The power loss does not loss, that is utilized power. Of course, the power in RL dash the power in load equivalent resistance is considered as a mechanically power developed. Of course, that power is converted to mechanical. Of course, that mechanical power is run that particular load. Of course, that load is equivalent to electrical resistance as R2 dash into 1 by S minus 1, where R2 dash is the rotor resistance. Of course, S is the slip of the three-phase induction motor. You know very well the slip of induction motor. Why the slip is considered in induction motor? Yes, the induction motor never runs with the synchronous speed. Of course, that is the first principle you know very well, right? So basically, the particular motor never runs with the synchronous speed. So the induction motor rotor speed is always slipping from the reference speed. What is the reference speed given to this? Synchronous speed, right? The rotor speed is always slipping from the synchronous speed. That slip speed considered, that slip speed divided by synchronous speed is considered as a slip, of course, right? Of that S is considered as a slip of the induction motor. Understand? Now, if it's mechanically power developed, of course, this power is utilized to run the mechanical load, right? Of course, this power depends on the power loss in RL dash. The RL dash depends on R2 dash and slip. Understand? So, very clearly we can understand the mechanically power developed depends on the rotor current, of course, and R2 dash and slip of the induction motor. So, in this equivalent circuit, the input current is I1 here, and this core current is I0, of course, there is a no load current, and this we considered that is I2 dash. There's a rotor current. That I2 dash is flowing through this, and of course, this I2 dash is flowing through the load equivalent resistance. Then easily you can estimate what is the power in RL dash, right? Of course, this I2 dash current is flowing through this. What is the power in RL dash? That is, I2 dash square into RL dash. That is a per phase power. Of course, for 3 phase, 3 into that. Understand? So, in this case particularly, there is one thing missed. You see, from the first to last, you can observe which one is missed here. Where is the rotor core losses? Where is the rotor core losses? Yes, that is missing here. Stator core loss is there. The power loss in R0 is considered as a stator core losses. But where is the rotor core losses? Here only rotor copper loss is there. The power loss in R2 dash is considered as a rotor copper loss. Where is the rotor core loss? Yes, we considered. But that's very small. The rotor core losses are very, very small. So that is neglected. That is neglected. Why that is small? Why that is small? You know very well. You know very well. The rotor currents depends upon the slip speed. The slip speed is very small. Understand? Of course, the slip speed is very small, so the frequency of rotor current is very, very small. The frequency of rotor current for positive sequence currents, it is about 2 Hz, 1.5 Hz, 3 Hz, like that only. For this much of 2 Hz, 3 Hz, the core losses, that means core losses means magnetic losses, that is the hysteresis losses and eddy current losses are very, very less, very, very negligible. That is the reason the core losses are negligible. That is the reason here we are not mentioning the core loss, rotor core losses. Only we mention the stator core loss. And again, which is missed, mechanical losses are missed here. Of course, mechanical losses are not mentioned in the equivalent equivalent circuit, that is separated. Yeah, from this mechanically power developed, the mechanical losses are subtracted. Finally, you can get the output of the motor. Why the mechanical losses are not mentioned in the equivalent circuit means mechanical losses depends on mechanical resistance like friction, windage, like that. Not depends on electrical resistance. That's the reason that is separated. Understand? So, from mechanically power developed, the mechanical losses are subtracted, so you can get the final output of the motor. Understand? So, here I clearly mentioned that the mechanically power developed PM is nothing but for 3 phase, this is only the single phase, for 3 phase means 3 into 3-phase. How much current is flowing through this RL dash? I2 dash square. And the resistance, what is the resistance here? RL dash. RL dash. Yeah, this is a mechanically power developed. Of course, here RL dash depends on, yes, R2 dash into 1 by S minus 1. Right? If the slip is 0, of course, if the slip is 0, when the slip is 0, if the rotor rotates at synchronous speed, it's not possible in induction motor. Of course, if slip is 0, it's not possible. But I assume that, of course, S is equal to 0. Then what happened for RL dash? If S is equal to 0, put S is equal to 0 here. 1 by 0, it gives infinity. So that RL dash is equal to infinity. If RL dash is equal to infinity, right, then this particular thing is open. If this particular thing is open, then what is the current I2 dash here? In open circuit, the current is 0. So the current through this RL dash is 0. So that if the current through the RL dash is 0 means PM, mechanically power developed, is 0. That means you see that PM is equal to 0. What's the PM? Mechanically power developed, which is utilized to run the mechanical load. When that is 0? When S is equal to 0. Right? Suppose if S is equal to 1, I considered S is equal to 1. When the S is equal to 1, slip is equal to 1. When the slip is equal to 1, you know very well if the rotor is at standstill condition. If rotor is not rotating, NR is equal to 0 means slip is equal to 1. Right? So then if slip is equal to 1, put S is equal to 1 here. What happened? 1 by 1, 1, 1 minus 1, 0. So RL dash is equal to 0. If RL dash is equal to 0, if RL dash is 0 here, then what's the mechanically power developed? 0. Mechanically power developed is 0. Understand? So here I considered that. So the particular induction motor is running in between S is equal to 0 and S is equal to 1. At S is equal to 0, no mechanically power developed. At S is equal to 1, no mechanically power developed. In between S is equal to 0 and S is equal to 1, there is a mechanically power developed. Suppose if I considered S is equal to 0.04, S is equal to 0.04, then what is the RL dash here? I can say R2 dash, of course R2 dash is considered as a, yes, I can consider this is 2 ohms. R2 dash is 2 ohms. S is equal to 0.04. Then what is the RL dash, tell me? RL dash is equal to, yes, 2 into 1 by 0.04 minus 1. Of course, you know that 1 by 0.04 is nothing but 100 by 4. This is nothing but 25. 25 minus 1 is 24. 24 into 2 is nothing but 48. 48 ohms. Understand? When slip is equal to 0.04 at R2 dash is equal to 2 ohms, then the corresponding RL dash is there, 48 ohms. So there is a current I2 dash as well as RL dash as well as mechanically power developed. So that in between S is equal to 0 and S is equal to 1, the slip is like that, then definitely there is a mechanically power developed. If there is mechanical power developed, then automatically the particular load is running. Understand? So here I consider that if the slip is small, small range, generally in full load conditions, the induction motor slip is small. At starting, the slip is high. Starting means, the speed, 0 speed to rated speed. If the motor pick up the speed from 0 to rated speed, that period is called as a starting period. Is it right or not? Starting means that is only. If the motor speed picks from 0 to rated speed, that particular period is called starting period. In starting period, the slip is high value like 0.9, 0.2, 0.7, 0.8, 0.5, like that. When the motor runs at rated speed, if the motor runs at rated speed, then the slip is considered as a very small, like 0.03, 0.04, 0.05, 0.0, like this, 1% to 10% like that. So in running conditions, full load conditions, the induction motor slip is low. At starting period, the slip is high. Understand? So here I consider that S is equal to 0, the PM is 0. PM means not Prime Minister, it is a PM is mechanically power developed. S is equal to 1, at S is equal to 1, the mechanically power developed is 0. So at smaller values of slip, I consider at small values of slip of S is small, then the mechanically power developed is directly proportional to slip. Directly proportional to slip. Suppose at larger slips S is large or high value, then the mechanically power developed is inversely proportional to slip. Yeah, from the power equations we can conclude these matters. Of course, this is derived forms. Definitely that can be derived. How that can be derived, yeah, PM is equal to 3 into I2 dash square into RL dash. Instead of I2 dash, you can put V phase divided by this particular resistance, total impedance. Then you can get the I2 dash. RL dash is nothing but this one. This total thing is substituted here. The PM is in terms of V phase, R2, X2, R1, X1, like that. So like that, this particular derivation, after derivation, we conclude the matters, conclusion matters. The mechanically power developed at S is equal to 0 is 0. The mechanically power developed at S is equal to 1 is 0. The mechanically power developed is directly proportional to slip when the slip is smaller value. When the slip is smaller value, if the induction motor is running at rated speed, running at full load speed, then we consider that is a small slips. When this particular slip is high value, yes, if the induction motor at starting period means 0 speed to rated speed. This particular period is called a starting period. In the starting period, the slip is high value. If the slip is small value, then the PM means mechanically power developed is directly proportional to slip. If a slip is high value, then the PM means mechanically power developed is inversely proportional to slip. Now we have the number 1, number 2, and this is number 3, and this is number 4. These are the 4 important conclusions. Yes, from these conclusions, we can draw power slip characteristics, or we can say power speed characteristics. Understand? So like this, we can simplify the power equation. So from these conclusions, what we conclusions here, yes, the mechanically power developed. What is the mechanically power developed, sir? Yes, actually the power is utilized to run the mechanical load which is connected to induction motor, right? Whatever may be the load connected to induction motor, of course that load must be running by this power, mechanically power developed. That mechanically power developed depends on the rotor current I2 dash and the load equivalent resistance RL dash. Of course, RL dash formula, this is very important. What is the formula of RL dash? Load equivalent resistance of 3-phase induction motor is nothing but R2 dash into 1 by S minus 1. Yes. Yes, you considered from this mechanically power developed, you conclude the 4 important points here. At slip is equal to 0, the mechanically power developed is 0. At slip is equal to 1, the mechanically power developed is 0. When the slip is small value, you know very well, the slip is small when the induction motor is running at rated speed or full load speeds. In that particular condition, the mechanically power developed is directly proportional to slip. If the slip is high value, when the slip is high value for 3-phase induction motor, you know very well, if the induction motor is at starting like the motor picks speed from 0 to rated speed, that period is called as a starting period. At starting period, you know very well, the slip is high value. If the slip is high value, the mechanically power developed is inversely proportional to slip. Of course, these 4 conclusions can be derived, can be estimated, can be approximated from this equation. Here I am not interested to derive that particular equation. Of course, in the next classes I will derive the particular equation if necessary. Understand? Yes, from these conclusions, simply I can draw what is the power slip characteristics or power speed characteristics. Yes. Of course, we can draw very easily, right? Yeah, just you remember the 4 important conclusions. Number 1, 2, 3, 4. Now I erase this one, right? Come on. Yes, you got that. The 4 important conclusions regarding mechanically powered developed is, you see, number 1, at S is equal to 0, the PM is 0. Number 2, at S is equal to 1, the PM is 0. Number 3, small values of slips, the PM is directly proportional to slip. High values of slips, the PM is inversely proportional to slip. These are the 4 important conclusions, right? Okay, then take the mechanically power developed on y-axis. Mechanically power developed on y-axis. On x-axis, take the slip or speed. Of course, the slip or I considered the slip is equal to 0 here, the slip is equal to 1, the slip is increasing from 0 to 1. When slip is equal to 1, what is the rotor speed of the induction motor? 0. When slip is equal to 0, what is the rotor speed? Equal to ns. Of course, this is not possible. This position is not possible. S is equal to 0 means nr is equal to ns. The induction motor never runs with the synchronous speed. Of course, in the graph, that point is, I mentioned that. At that point, the mechanically power developed is 0. No doubt. There is no action. At S is equal to 0, there is no action because mechanically power developed is 0. At S is equal to 1, there is no action because the rotor is at standstill. In between S is equal to 0 and S is equal to 1, yes, the motor action started. What is the action of the motor? Yes, the motor runs the connected mechanical load. Understand? Of course, the mechanical load may be that is one mission, that is one rolling mission, that is one fan, whatever may be the mechanical load connected to this motor. That mechanical load is running by this particular power, mechanically powered. This mechanically powered developed produces the particular torque, twisting moment. Now, after next classes, I will discuss what is the torque equation and everything, right? Okay. Then you see that. Come on, you see that this is S equal to 0, I consider this 0.1, like is a 0.2 and so on like this, 0.5 and this 0.9 and so on. S is increasing from 0 to 1. And here the speed increasing like this is a speed and this is a slip. The slip increasing here from this point to this point, speed increases from this point to this point. Well done. Come on, mister, tell me. At S is equal to 0, what is the PM? 0. That means the curve is starting from 0. PM is 0. Yes, these are all small slips, you know. This 0.1 means the small slip. If the slip is small value, then PM is directly proportional to slip. PM and slip both are directly proportional. If the two variables having directly proportionality, then what is the graph between those two variables? Is a straight line passing through the origin, you know very well, right? Any two variables are having directly proportionality, then the graph between those two variables is nothing but straight line passing through the origin, right? So the graph, for a smaller slip, so the graph is a straight line like this. Yes, once you reach the higher values like this, higher values of slip, then the PM is inversely proportional to slip. If the two variables have inversely proportionality, then the graph is rectangular hyperbola, not straight line. If the two variables having inversely proportionality, like this, PM is inversely proportional to slip, where PM and slip both are inversely proportionality, the graph between PM and slip is is rectangular hyperbola, not straight line. Understand? So that if the slip is higher value, then this is a rectangular hyperbola like this. So whenever S is equal to 1, the slip reaches to 1, the PM is 0. PM is 0. If S is equal to 1 here, what is the PM? 0. At S is equal to 0, PM 0. At S is equal to 1, PM 0. In between S is equal to 0 and S is equal to 1, yes, there is a PM. There is a PM means, what is a PM here? Mechanically power developed. Of course, that power is utilized to run the mechanical load which is connected to motor. Understand? Yes, of course, you know that here in this graph you can see the mechanical power mechanically power developed reaches the maximum value at one slip. Of course, this PM reaches maximum value at one slip. That is PM maximum. Yes, at this point, what is a slip that considered as a slip at maximum power? This is a very important question, of course. What is a slip at maximum power? We can derive in the next classes. Not a hurry. First, you have to understand what is the curve here. Right. Anyway, of course, this is nothing but the slip at maximum power. MP. MP ante. You see that the MP means maximum power. The S means slip. MP means maximum power. Slip at maximum power. Yes, that can be derived. That can be derived by using this PM equation. PM equation. From the PM equation, you can derive what is the slip at maximum power. To find the maximum value or minimum value, definitely you can use a particular thing. What is that? Yes, application, derivative application. The derivatives are well known to find out the maximum value or minimum value for single variable functions, single independent variable functions. Like this, once you know the PM equation, from that equation, of course, the slip is the variable there, the single variable. Of course, the PM is differentiated with respect to slip. That equation differentiated with respect to slip. What happened? Yes, at last one condition is obtained. Of course, that condition gives the slip at maximum power. Yeah, the power slip characteristics. Of course, in this case particularly, this straight line, this particular region is called as a stable region. Stable region. Yes, this rectangular hyperbola region is the unstable region. Unstable region. This thing totally thing is a starting period. Of course, this particular thing, the load power. Of course, the mechanical load is connected to motor. Of course, the motor producing this much of power, the load having separate power. Of course, that's called as the load power. Yes, that load power, this is a dotted line is the load power, constant load power is there. Of course, that we consider as a PL. Now, the power produced by the motor, this is the power produced by the motor at different slips. Now, the power produced by the motor and the mechanical power of the mechanical load, both are coincides at this point and at this point. Right? Now, which one is a stable point? Which one is the unstable point here? Yes, the stable point is, this is a stable point. That is a full load power. That's called as a full load power. This is called as a full load power. This point is unstable point, of course, because why this is unstable point? Yes, at starting, the heavy rush of currents are there. That motor draws heavy rush of currents. Understand? So basically, this is unstable. Of course, this particular motor producing a sufficient load torque. But the thing is, at this point, the speed is very less. Is not rated speed. As well as the current is heavy. That's not rated current. So the motor is operated at this particular stable point. Of course, at this stable point, you consider as a rated slip. That's called full load slip. Yes, that is SF. What is SF here? The full load slip. Now, this is called power slip characteristics or power speed characteristics. Yeah. Do you understand? Yeah, it's very easy to understand because you must remember the 4 important conclusions from the mechanically power developed. Just you have to revise the particular thing. Yeah, from equivalent circuit, yes, if something power is given to the stator of induction motor, that is a stator input. The stator input power is distributed like this. Some power is lost at R0. Of course, that power is called stator core losses. Some power lost at R1. Of course, that power is stator copper losses. Some power lost at R2 dash, that's the rotor copper losses. The remaining power is converted as mechanically power developed. Of course, that power converted as mechanically power developed to run the load. Of course, that RL dash is nothing but R2 dash into 1 by S minus 1. That's called as the load equivalent resistance. whatever be the mechanical load connected to the motor, of course that mechanical load is converted to equivalent electrical resistance. What is that? That is nothing but R2 dash into 1 by S minus 1. Right? If some current I2 dash, there's a rotor current is flowing through this resistance, some power is there, of course I2 dash square into this resistance into 3, because that's a 3-phase motor, so that the mechanically power developed equation is there. Of course, from that equation we conclude the 4 important points here. From these 4 important concluded points, we can draw the power slip characteristics, or we can say there's a power speed characteristics. Understand? Right, well done. In the next class, I will discuss about the remaining points on the power slip characteristics and power speed characteristics. So after that, we will discuss about the torque equation and everything. And we have to analyze the 3-phase induction motor by using equivalent circuit, by using per phase equivalent circuit. This is very important. Once you know the per phase equivalent circuit, from this we can analyze the 3-phase induction motor. 3-phase induction motor is nothing but RL circuit. 3-phase induction motor is nothing but RL circuit. Once you know the RL circuit, right, then easily you can analyze the 3-phase induction motor in terms of speed, in terms of torque, in terms of power, and 3 are related. You know what is the relation between these 3? For any rotational motor, you know that the relation between these 3 is nothing but torque is equal to power by angular speed, or power is equal to torque into angular speed. Understand? You know that, yes, that power or torque is equal to power divided by angular speed, omega. Omega is nothing but 2 pi ns, you know that. Yes. So this particular 3 important, torque, power and this angular speed. These 3 are related for any motor. Understand? Yeah. In the next classes, we will discuss about the remaining things and interesting things about the 3-phase induction motor. Understand? And of course, we have to discuss about what are the objectives, different objectives of the 3-phase induction mission. Now, the 3-phase induction mission objectives are basically, you know that it acts as a motor, it acts as a generator, it acts as a brake. Understand? Like this, these are so many objectives are there. Okay, we'll discuss one by one. So, my dear students, all the best.